Hey guys, welcome back to another lecture video for Chem 115. In this lecture video, we are going to learn how to rank the molar solubilities for a given set of substances. And so by ranking the molar solubilities for these substances, we're going to be able to understand which slightly soluble, mostly insoluble substance is going to be more soluble compared to another. So let's get started. When you guys are ranking these molar solubilities, you guys can do so by using the KSP. So the KSP, if you guys recall from the first lecture video, it is the product of the molar solubilities of the ions that's produced when a specific slightly soluble, mostly insoluble compound dissociates. And so, since the KSP is a product of the molar solubilities raised to the coefficient, and the coefficient can be found from the general chemical equation, from the balanced chemical equation, we can go ahead and set up a mass action expression to determine the molar solubility. And so remember that the molar solubility is denoted as the S, or the change that's in our ICE table. Okay. The one thing that I do want to mention is that the KSP, the actual value, and I'm just talking about the value here, the value of the KSP does not equal to the value of the molar solubility. And so when you guys are looking at these KSP values, don't automatically rank them based on the actual value of the KSP. You guys need to determine the actual molar solubility. Now there are some instances in which you can do so. You can use the magnitude of the KSP to gain some inferences as to the trend of which slightly soluble compound is more soluble compared to another. And we'll look at that in just a second. But the main point that I want to convey is that the actual value of KSP is not the same as the molar solubility. Okay. All right. So we're going to go ahead and take a look at a couple of situations. We're going to see how we can determine the molar solubility, and we're going to learn how to rank them based on increasing or decreasing order. And so we're going to look at two situations. And the first situation that we're going to discuss is when the slightly soluble, mostly insoluble salt contain the same number of ions. And the number of ions that I'm referring to is on the product side. Okay? So we're going to see, we're going to look at how we can determine the molar solubility and see if there's any trend that we can kind of extract. And so this is the main question that we're going to address. We're going to rank the ionic salts based on increasing molar solubility. And so when you're going from increasing molar solubility, you want to know what's the lowest, so the least soluble. So if it is the least soluble, then it's the most insoluble. All the way to the highest. And in this scenario, we're going to, so if we're talking about the highest molar solubility, then it's the most soluble. And the least insoluble. So these terms just kind of switch around. And so when you're talking about solubility, just keep in mind it's those ions that's separating. in the solution. So if it's not soluble, then it's going to clump up and just like form a solid, form a precipitate. And not a lot of ions are going to be released. But if it is more soluble compared to another, then there's more ions that's being released into the solution. All right, so what we're going to do is we're going to take a look at three substances, and all of these substances are different. They have different cations, different anions, and the KSP value is already given to us. And what we're going to do is we're going to use this KSP to determine the molar solubility of each of these slightly soluble, mostly insoluble compounds. And then we're going to go ahead and rank them. And to do so, we need to go ahead and set up, a chemical equation and an ice table and a mass action expression and solve for the value of S. Now, before I start going through that process, I want you guys to take a look at these substances. And so we're just going to look at the chemical equations for now. So if we have AgI, and I'll go ahead and work them just maybe over here then. So if we have silver iodide, okay, and this is the slightly soluble, mostly insoluble salt, and when a small portion of it dissociates, it's going to produce silver ion and iodide ion. And they're all going to be aqueous in phase. Now, if we're looking at the second substance, copper 1 iodide, when they separate from each other, when a small portion of that slightly insoluble salt separates from each other, it's going to produce copper 1 ion and iodide ion. And last but not least, if we look at calcium sulfate, when this slightly soluble, mostly insoluble substance, when a small fraction of it dissociates, it's going to produce a calcium ion and the sulfate ion. And so these are the three chemical equations that is representative of the separation of these slightly soluble, mostly insoluble substances. Now, there is a trend I do want to mention. If you look at AgI, CuI, and calcium sulfate, how many ions in the products does each of them produce? All right. And so if we're looking at these two, if we're looking at the products, there's 2 ions. Okay? And it's a 1-to-1 ratio. And that's why, so here this is a 1-to-1 ratio. There's 1 silver for every 1 iodide. Add up the numbers together, and there's 2 ions. And I'm going to scoot this down just a little bit just so I can have room to write. And if you guys look at copper 1 iodide, once again, we have 1 copper for every 1 iodide, and the sum of those coefficients produces 2 ions. And same thing here, 1 calcium and 1 sulfate. And so overall, we produce 2 ions. And so it turns out that if you have the same number of ions that's being produced among the set of slightly soluble substances that you guys are comparing, then you guys can go ahead and use the magnitude of the KSP to create some type of inference with respect to their molar solubility. And so here, I kind of wrote it down. If the number of ions produced for all of the substances that you're trying to rank if the ions produced is the same for all substances that's being compared, then you can rank the molar solubilities based on the magnitude of their KSP. Okay? And I'll show you how this is possible. But for now, because the number of ions I produce is the same, I'm going to go ahead and apply this rule, and I'm going to predict that the calcium sulfate, since its magnitude is closer to 0 times 10 to the negative 5, so that's higher than times 10 to the negative 17. So I'm going to predict that calcium sulfate is the most soluble of these slightly insoluble, mostly insoluble substances. And so I'm going to predict that it's going to have the highest molar solubility. Just because its magnitude is times 10 to the negative 5, which is larger than the other values for the KSP. And so I would have to say that based on the numbers that I'm seeing here, copper 1 iodide is probably in the middle, and the substance that's the most insoluble, the substance that has the least molar solubility, is going to be AgI. So this is going to be the least soluble of all of these slightly soluble substances. Okay. So, excuse me. So AgI will have the lowest molar solubility. And I'm just basing this on the magnitude of the KSP. Just because the number of ions they produce is the same. So that is the requirement. Okay. And I'm going to go ahead and prove this. I'm going to prove this to you. And so to determine the molar solubilities, we're going to go ahead and do the long way. So here we have AgI. And we know that it's going to produce Ag plus and I minus. I'm not going to write the physical state of matter. Everything is aqueous on the right-hand side. And so here I have ice, the ice table. And I know that some amount of the starting material, which is the silver iodide precipitate, some small fraction of it is going to dissolve to produce silver and iodide. And so the equilibrium expression, the equilibrium concentration for silver and iodide is the same as the molar solubility of silver iodide. And so if I were to write a mass action expression, this would just be S times S, which is going to be S squared. And so therefore to solve for the molar solubility, it's going to be the square root of the KSP. And so I'm going to go ahead and repeat the same procedure for copper 1 iodide and calcium sulfate. Okay. I'm not going to plug in any numbers yet. I just want to look at the equations and the ice tables and all that stuff. So here we have copper iodide. That's our solid. And then it'll produce the copper plus and the iodide minus. Once again, I'm going to exclude the physical states of matter just because I know that everything here is aqueous. So this is plus S plus X plus S. And so it turns out that the equilibrium concentration for copper is the same as the molar solubility of copper iodide. And the equilibrium concentration for iodide is the same as the molar solubility of copper 1 iodide. Now, if you guys write the mass action expression, and if you guys write the mass action expression, it's going to be S squared, and I'm going to square root both sides, and the molar solubility, which is represented by S, is going to equal to the square root of the KSP. All right, and then I'm going to go ahead and do one more set for calcium sulfate, and then we're going to go ahead and start comparing and contrasting. Some of you guys might already see it. So calcium sulfate, we know that this is the slightly soluble substance, and so it's going to produce calcium ion plus sulfate ion. Here we have I, C, and E. We know that calcium sulfate is going to have some amount of molar solubility, and so some portion of it is going to be, some portion of it will dissociate to produce some amount of calcium and some amount of sulfate. And it turns out that the equilibrium concentration of calcium is equal to the molar solubility of calcium sulfate, and the equilibrium concentration of sulfate is equal to the molar solubility of calcium sulfate. Okay. And so the KSP, if you guys do the mass action expression, remember this is 1 to 1, it's going to be, S to the first times S to the first, which is going to be S squared. And so if I solve for the molar solubility, which is KSP, if I solve for the molar solubility, I have to take the square root of both sides. And the molar solubility for calcium sulfate is defined by the square root of its KSP. Now, if I zoom out and I compare my work for all three, and I want you guys to notice that there is no initial value, right? So if you look at the problem, it didn't give us any initial value, just only gave us KSP. So there's no point for us to put anything in the initial value in our ICE table. Okay. So I'm just going to go ahead and blank all of this out just to address that question if you had it in the back of your mind. So if you guys are looking at the equation that will determine the molar solubility of AgI, CuI, and calcium sulfate, it's the same expression. You're simply taking the square root of all the KSPs. And so since the way that we're solving, excuse me, the molar solubility is through the same method, the relative ratios of each other is still going to follow the trend. Okay. And so let me go ahead and solve this all the way through, just so that you guys can see the actual numbers. So here you have 8.5 times 10 to the negative 17 for silver iodide. Okay. So I'm going to take the square root of square root of 8.5 times 10 to the negative 17. And so I'm going to go ahead and do that in my calculator real quick. Just give me a second. So 8.5 times 10 to the negative 17, okay, so I'm going to get 9.22 times 10 to the negative 9. Okay. And this is going to be my molar solubility. I'll highlight that. And so if I determine the molar solubility of copper 1 iodide, I'm going to take the square root of 1.3 times 10 to the negative 12. So if I plug that into my calculator, square root of 1.3 times 10 to the negative 12, that's going to give me 1.1 times 10 to the negative 6. Oops. So the molar solubility is going to be 1.1 times 10 to the negative 6 molar. And that's going to represent the molar solubility for calcium, copper iodide. And last but not least, for calcium sulfate is going to be 4.9 times 10 to the negative 5. And so I'm going to go ahead and plug in 4.9 times 10 to the negative 5 into that expression. So I'm going to take the square root of 4.9 times 10 to the negative 5. And what I get is 7.0 times 10 to the negative 3 molar. And so this is going to represent the molar solubility of calcium sulfate. So now that we have their actual values, all we need to do is just compare the magnitudes, since the magnitudes are all different. And so I'm going to zoom in just a little bit here so we can see it just a little bit better. And so I'll go ahead and write here AgI and copper I. Okay, so that's this guy right here, copper 1 iodide, silver iodide, and then this is going to be calcium sulfate. Okay. So if you look at the items that I circled, which of the following will have the highest molar solubility? Okay. And so based on the actual molar solubility, based on these actual numbers, calcium sulfate will have the highest molar solubility. That means that even though it's a slightly soluble, mostly insoluble substance, right? It's a precipitate. It will dissolve more compared to the other substance that it's being compared to, such as AgI and copper 1 iodide. And so if you guys look at the magnitude here for copper 1 iodide, it's -6. This one is -9. So -6 is much greater than -9. And therefore copper 1 iodide is going to be the substance that's in the middle. And the last is going to be AgI. Okay. So this is telling us this is the least soluble because it has the lowest molar solubility. Okay. So if you guys have a precipitate that's composed of silver iodide, it really does not want to lose its ions. It really doesn't want to dissociate. It's going to stay as a precipitate most of the time, but there's still some that will dissolve. 9.22 times 10 to the negative 9 is the concentration of the silver and iodide that's present in that solution. So it's not a lot, but there's still some. Okay. Now, this ranking that I did based on the actual value for the molar solubility, if you compare that to what I predicted, it's the same. And I'm just going to make sure to demonstrate this point by copying it. Okay, so this is what I predicted from magnitude of the KSP. And so if you look, it's the same answer. And so this is the proof, this is the validation that I just wanted to show you guys that you can use to to rank the molar solubilities of a given set of slightly soluble substances. But you can only do this, you can only use the KSP to rank the molar solubilities when, or not so much when, but if and only if the number of ions that's being produced by each of those substances is the same. So 2 ions, 2 ions, 2 ions. Okay. Now it doesn't have to be 2, 2, 2. It can be 3, 3, 3, 4, 4, 4. But the main point is that it has to produce the same number of ions amongst all of them. Okay. All right. So hopefully that makes sense. So this is the trend that we can use for this specific scenario. Okay. All right, so we're going to go ahead and look at another scenario. So what if our salts do not have the same number of ions? Okay. So if the slightly soluble, mostly insoluble salt produces different number of ions, how can we rank the molar solubilities? Okay. Well, long story short, if they have different number of ions, then you must, actually I think I wrote it down here. Yeah, I did. And so let me just go ahead and read what I wrote. If the number of ions produced from each of the substances that you're comparing is not the same, then you cannot rank the molar solubilities of the substances based on the magnitude of their KSP. And the only thing that you can do, so there's no approximation, right? There's no shortcut. The only thing that you can do is to solve for the actual value of the molar solubility. So you actually have to build your ice table, your balanced chemical equations, and your mass action expression for KSP, and then just simplify that mass action expression down to the point where you can solve for S, or the molar solubility. Okay? And so you actually have to perform all of those steps. And then after you perform all of those steps, then and only then can you rank their molar solubilities by comparing their values. Okay? And so let's go ahead and start. And so in this scenario, in the first scenario that I gave you, I said increasing. I'm going to change it up for this one. It's going to be decreasing molar solubility. And so we're going from highest to lowest. Okay. So we're going from the most soluble to the least soluble. Okay. And once again, we're comparing their molar solubilities. So let's start. And so if you guys look at the KSP values, these are really, really, really small. Negative 57, negative 51, negative 73. And so, just looking at these KSP values, since it's so far less than 1, it's very, very, it's super less than 1. I can't emphasize that enough. If you guys are thinking about it in terms of a chemical equation, the equilibrium is really, really, really favoring the substance on the left side of the arrow, which is going to be your reactant. And so what this is telling you, what this KSP is telling you, is that, when the system reaches equilibrium, when you pour those substances together, you are going to form a solid. And you're going to form a lot of it, right? And so let's go ahead and start. So we're going to go ahead and do copper 2 sulfide. So this is going to be copper 2 sulfide. Okay. And that's solid. And so here the KSP, I'll just write it above the arrow, is 6.0 times 10 to the negative 57. So the KSP is far, 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 far less than 1. So we know that the equilibrium will favor the formation of the reactant, which is a solid. So you're going to get a lot of precipitate. And so because the system is always at equilibrium, the reverse reaction will occur, and the forward reaction will also occur, such that we do still get trace amounts of the copper 2 ion and the sulfide. Okay. Do we know how much? Well, that's what we're going to figure out, right? And very similar to what I did in the previous example, I can go ahead and set up an ice table to represent the initial change in equilibrium. And so since the problem only gave us KSP values, there's no initial amount at all for any of these substances. And so typically for this chapter, if there is an initial amount, then it's either a common ion effect or simultaneous equilibria. And we'll talk about simultaneous equilibria in a future lecture video. Okay. So those are like the only two instances within this chapter in which you guys will see an initial amount. Otherwise, everything else is pretty much ignored. And you can get that information, you can glean that information from the problem, right? The problem will not tell you that, or it won't imply that there was an initial amount to begin with outside of the common ion effect and simultaneous equilibria. All right, so let's start. So we have minus S plus S plus S. This is a 1-to-1 ratio, so there's 1 and 1. Okay. And so we've seen this before, so at equilibrium, the concentration of copper and the concentration of sulfide is the same as the molar solubility of copper 2 sulfide. And so therefore the KSP is equal to S squared, and the molar solubility S is equal to the square root of KSP. Okay, so that is our expression. If we want to solve for the actual KSP, if we want to solve for the actual molar solubility, we're going to plug in that 6.0 times 10 to the negative 57 into where you see KSP. And so the square root of this value, I'm going to go ahead and plug it into my calculator. Square root of 6.0 times 10 to the negative 57. That's going to give me a molar solubility that is 7.7 times 10 to the negative 29. All right. And so remember that the molar solubility, S, is equal to the equilibrium concentration of copper and sulfide. And so we really don't have a lot of copper ions or a lot of sulfide ions in solution. Times 10 to the negative 29, that's larger than a mole, right? Remember, a mole is times 10 to the positive 23. In terms of magnitude, I'm going to take the absolute value. So 29, that's basically 28 zeros before you hit the 7. Whereas in the mole, you have 22 zeros, and then you hit the 6. Okay, it's a very low amount. All right, and so let's go ahead and do the next one. So Ag2S. So here we have silver sulfide. Now, if you guys are looking at the chemical equation for silver to sulfide, it's a 2-to-1 ratio. So there's 2 ions for every 1, 2 silver ions for every 1 sulfide ion. And once again, if we do the ice table, nothing in our initial, some amount of your silver sulfide will dissociate to produce the ions, and we get 2 times S and S. And so at equilibrium, we just get 2S and S. And remember, this is solid, so we're just going to ignore all that stuff on the left-hand side. And so when we build our mass action expression, it's just products over reactants, but since the reactants is a solid, that's completely ignored. And so therefore we are going to put in, 2s times this by s, but make sure that you guys are using the coefficient to represent the exponent on this mass action expression. So it's going to be 2s squared and then s to the first power. And so we're going to distribute that square to the number and the letter. So that's going to give us 4s squared times s to the first. And that's going to simplify to 4s to the third, which equals to the KSP. And so I'm going to go ahead and solve for the molar solubility. And if you perform the algebra, you're going to divide the 4 first. So it's going to be KSP divided by 4. And then you're going to get rid of this third, this exponent, this cube, by taking the cube root of both sides. And that's what I'm representing here. So I'm just skipping some steps. Okay. All right, so if I wanted to solve for the molar solubility, which is S, I'm going to go ahead and plug in 6.0 times 10 to the negative 51. So here I'm going to 6.0 times 10 to the negative 51. I'm going to divide that by 4 first, and then the result, I'm going to I'm going to cube root the result. So 6.0 times 10 to the negative 51. Divide this by 4. That's going to be 1.5 times 10 to the negative 51. And then I'm going to go ahead and cube root it. And so when you guys are, if you guys are having problems taking the cube root, so you guys can always set up, so 6.0 times 10 to the negative 51, you guys can perform this operation first, and then you can go ahead and raise it to the 1/3 power. So this is like the caret sign in your calculator. And so that's the same thing as a cube root. And so the molar solubility is going to be 1.1 times 10 to the negative 17 molar. Okay. And so here the molar solubility is 7.7 times 10 to the negative 29 molar. And so notice how, if you guys are looking at the KSP value, maybe I should write the KSP for this one. So the KSP is equal to 6.0 times 10 to the negative 51. So notice how the KSPs, they're different. And if you guys are looking at the result, so to speak, we have times 10 to the negative 29, we have times 10 to the negative 17. And so I guess between those two, the trend kind of still holds, like negative 51 is much closer to 0 compared to negative 57. If you guys are looking at the molar solubilities, negative 17 is closer to 0 than negative 29. And so that's only because we're comparing we're comparing two. But what if we incorporate like a third? Okay, so if you guys look at this specific substance, is 1.1 times 10 to the negative 73. And so we're going to determine what the molar solubility is for this substance. And then once we determine the molar solubility for the substance, then we'll go ahead and look at all those values and start ranking them in decreasing order. So we have Bi, 2, S3. And so the KSP is going to be 1.1 times 10 to the negative 73. And so here I have 2 BIs. Plus 3. Here I have sulfides, and I have 3 of them. So for every 2 bismuth, I have 3 sulfides. Therefore, I have these guys as my coefficients. So once again, ice table, nothing, nothing, nothing for initial. Problem didn't really give us anything. It just gave us the KSP. I know that some amount of this will be consumed, and it's 1, right? So if you have 1 BiS2 or Bi2S3, you have minus 1S. Okay. So here we have 2 times S, and here we have 3 times S. So here the equilibrium concentration for bismuth is going to be 2 times the molar solubility of Bi2S3, and the equilibrium concentration of sulfide is 3 times the molar solubility. And so we are going to build, now that we've built our ice table, we're going to go ahead and write the mass action expression. And so KSP is equal to 2S, that's the bismuth, times that by 3S, that's the sulfide. Now, since the coefficient is 2 and 3, we also have to make sure that it's incorporated in our mass action expression. And so here we get 4s squared times this by 27 s to the third. Okay. So I'm distributing the 2 and the 3. Okay. 2 squared is 4. 3 to the third power is 27. Okay, so that's 3 times 3 is 9, times 3 is 27. And so you guys can go ahead and combine these values. So 4 times 27 is 108. And s squared and s to the third is s to the 5. We're just adding those powers. And so if the KSP is 1.1 times 10 to the negative 73, that's going to equal to 108 times this by s to the 5th. So we're going to go ahead and divide by 108 on both sides. And then I'm going to 5th root my answer. Okay. Duplicate. Now, you guys don't have a 5th root function in your calculator. Maybe you guys do, depending on your scientific calculator. But another way for you guys to represent the 5th root, if you guys don't have the, it looks like this in your calculator. It looks like, okay. And so this is what you guys can use to determine any root. So 5th root, 9th root, 10th root, 13th root, whatever. Some calculators, in terms of how you guys plug it in, it's going to be a little bit different. So that's something that you guys kind of need to explore on your own. So personally for me to expedite that whole process and make sure that you guys are doing it precisely, go ahead and determine the value that's inside the parentheses, and then put the caret sign in your calculator, and then type in 1 divided by 5. And that's equivalent to the 5th root. And that's going to give you the molar solubility. So I have 1.1 times 10 to the negative 73. Divide this by 108. That's going to be 1.0185, etc., times 10 to the negative 75. And then I'm going to raise that to the 1 over 5 power. So I'm taking the 5th root, and I get 1.0 times 10 to the negative 15 molar. Okay, so this is my molar solubility for Bi2S3. And so if you guys are looking at, the KSPs, right, I'm going to zoom in just a little bit here. So the KSP for Bi2S3 is negative 73, KSP here is negative 57, KSP here is negative 51. And so if you look at the molar solubilities, it looks like Bi2S3 is the most soluble. If you look, it's times 10 to the negative 15, which is the highest value compared to 1.1 times 10 to the negative 17 and negative 29, or 7.7 times 10 to the negative 29. Just so that you guys can see this, I'm going to clean up my work. I'm going to summarize the results, and I'm going to align the KSP and the molar solubilities, just so everything is read in one screen, and I'm not moving everything. So here we have copper iodide, I believe. So, no, not copper iodide, it's copper sulfide. And so the KSP, I'm going to go ahead and put it in this column, was 6.0 times 10 to the negative 57, and its molar solubility, or S, let me see here, what was its molar solubility? It's 7.7 times 10 to the negative 9. Okay. And then my next substance was that silver sulfide, and its KSP was 6.0 times 10 to the negative 51. And then that's going to equal to 1.1 times 10 to the negative 17. And last but not least, we have Bi2S3. And the KSP was the smallest of the group, with an exponent of times 10 to the negative 73. Man, that's really small. And so this is really telling you that the equilibrium lies really far to the left, lies on the reactant side. And so here we have 1.0 times 10 to the negative 15 molar. Cool. So if you guys are looking at the magnitudes between KSP and the molar solubility, notice that this was the lowest KSP value amongst this set, yet its molar solubility is the highest. And so if you guys were ranking the molar solubility just based on the KSPs for this problem set, you guys are going to get your ranking wrong, just because the number of ions that each and every single one of these substances produces is different. So these two, or copper 2 sulfide, produces 2 ions. Silver sulfide produces 3 ions. And this substance produces 5 ions. And so if you have different number of ions, you guys cannot use the magnitude of the KSP to rank the molar solubilities. You guys have to physically calculate the molar solubilities from the KSP to arrive to your final answer. Okay. And so remember that the original problem is asking us to rank it in decreasing order. Decreasing order of solubility. And so we're going from highest to lowest. And so the highest molar solubility is going to be Bi2S3. S3. So Bi2S3 is the highest. Okay. So I'll just go ahead and put this as 3 for now, because we're going in decreasing order. And so the next, the one in the middle is going to be 1.1 times 10 to negative 17. That's going to be Ag2S. So this is going to be Ag2S. And then the last one is going to be copper 2 sulfide. All right. And so here in this case, the lowest is going, the substance that has the least molar solubility is copper 2 sulfide. And so if we would have to rank them, this would be like quote unquote number 1. Okay. And Bi2S3 has the highest molar solubility. And I'm going to go ahead and rank it number 3 because we're going in a decreasing order. Okay. And I'm putting these inequalities to demonstrate, the how the values compare relative to each other. So times 10 to the negative 15 is bigger than times 10 to the negative 17. Times 10 to the negative 17 is larger than times 10 to the negative 29. All right. So with that said, that pretty much completes this section in this chapter. The take-home message is calculate your molar solubility from KSP. And so if you recognize that you have, the same number of ions, then you can go ahead and use the KSP, the magnitude of the KSP, to rank the molar solubilities, whether it's increasing or decreasing. But if you have a mixture of, if the substances that you guys are comparing produces a different number of ions, then you guys have to perform the calculations and determine the actual value for the molar solubility. All right, so that's it for this lecture video. I'll see you guys in the next one. Bye.